Welcome to a KNAUER HPLC Columns tutorial with the topic widePore Reversed Phase Columns. So we already talked a lot about reversed phase in one other tutorial, but there is a special case where you can use similar phases, also reversed phases, but with wide pores. And we will talk here about why they are so special and when we can use it. So again, what is the widePore reversed phase model like? You use a stationary phase that is really unpolar or maybe a little like midpolar. You will see what I mean with that later on. But typically you also use the same as in reversed phase, but with wider pores in the silica gel material. The mobile phases you use are more polar, again like in reversed phase mode. And the analytes are larger biomolecules. So typically we are talking about proteins or peptides that can get really too big to be analyzed on a typical reversed phase column. And really important, they have to be water soluble because the mobile phase you are using here is polar and most often existing of water content and just a little bit of organic modifier. So the analytes have to be water soluble. Proteins, this is most often not a problem. For some peptides, this mode can't be used because they are not soluble. But why do we use now wider pores than for typical reversed phase applications for small analytes? So we have a packing material in our column. This is again a silica gel material, so a silica gel based phases. And I just made a schematic drawing for you. These are the pores in the material. So it's only schematic. Normally they are going through all the particle, but they have a typical diameter that is always named for a column. And when you now have an analyte that is a small molecule, what is typically used in reversed phase, you don't have any problem if you want to do a separation. To have a good separation, the molecule has to penetrate the pores. Otherwise, it just flows much too fast down the column and won't be retarded and won't be separated. It has to go these ways inside and outside and inside and outside again to have good interactions with the stationary phase. And for small molecules, it's not a problem. It goes in, it goes out. You have penetration of pores and retardation. But if you look at a larger biomolecule, for example, a protein, that maybe is soluble in your allo and not a problem, you use it just with the same method and column that you use for small molecules, and now you have the problem, it can't go inside the pores. It's too large. So it won't be retarded. You have no retardation, and you get effects like size exclusion. So if a molecule is too large for your pores, you have a size exclusion. That means that the analyte is eluting in the dead time or near the dead time of the system and the column because it's just not interacting well with your stationary phase. So this means you will need larger pores, of course. So if the pore gets larger, also these larger biomolecules can take the same way as the small molecules for the small pore materials. Okay, now you see here I made a drawing with the same material but larger pores. So now even for the larger molecules it's not a problem to get inside the pore. But we also have these materials with different modifications. So for a C18 or a C18A modification that you already know from our typical reversed phase material with small pores, there you will have the C18 chains brought on the material. And again, it's just a schematic drawing, but you can get an insight here why this is offered for rather small biomolecules. So if the biomolecule is around 2,000 to 5,000 Dalton, a C18A phase with large pores is okay because the analyte can penetrate the pores. If the analyte gets larger, it will get problems here because the pore, you see, gets smaller because of the C18 modification. And now you can use a C8 modification when the molecule gets larger. So we say around 5,000 to 20,000 Dalton, you can use a C8 modification on a widePore material. And if it's getting really large, you can use a C4 modification. And here we can use biomolecules up to 100,000 Dalton in size. So you see, the larger the molecule gets, the larger you have the pores to be. So the shorter the C chains on the material have to be, because otherwise they shorten the pores. And this is why I told you in the beginning, these are reversed phase materials, but sometimes we also use more polar ones, because a C4 modification is much more polar than a C18 one. But what is the mechanism now happening here? Maybe you already thought, okay, in the typical reversed phase mode, the modification is really dependent on the interaction of the chains between the molecules, the chains, and the rest cylinder groups on the materials. This is a little bit different for the widePore materials. Here, the separation mechanism really is only apparent because of the size of the pores. So typically, you first inject, and in the first step, you have an absorption of the proteins that you inject on the top of the column. You do this with aqueous mobile phases, sometimes also buffers, or most often buffers. And it's just a little organic content, or it's really only water. And then you get desorption and elution of the proteins. They get out of the pores again, and this you do by increasing in organic content and concentration of the mobile phase. So this is just an absorption and desorption mechanism, so it's really easy. And this is why there are not so many different column types on the market, but only C18, C8, and C4. And also the C18A one, because it can be used with pure water. At KNAUER, we have our Eurosil Bioselect phase. It's ideally made for these larger biomolecules, and it's really like our classical Eurosphere 2 column family, but it has larger pores. So you see, the characteristics are nearly the same, just the pore size here is larger. Typically, you use for small molecules 100 angstrom pores, and here it is 300, and therewith the specific surface also gets smaller. And here again an overview, the 4 modifications that we can offer, and you see also that the carbon content is some kind of lower than for a C18 phase with smaller pores. It's just caused by the smaller specific surface, so you don't get as many C18 chains chemically modified on a silica gel particle with larger pores. Okay, I hope you got an insight in the mechanism of our Eurosil Bioselect columns that are used for widePore reversed phase mode, and you now know how you can analyze your proteins that get too big for typical normal small molecule reversed phase applications.